Okay, thank you very much. And let me first recall one thing we've learned in Professor Wenn's lectures. He said that we have to learn category theory because it is really a very natural language. And what I want to show you is that category theory and really basic notions of category theory are the correct thing to address rather intricate objects, namely bulk fields in two-dimensional conformal field theory. Now, two-dimensional conformal field theory and fusion categories or modular categories, that's a very well-known connection. It appeared a little bit in Yasu's talk. So let's go back and look at a little bit of history to start with. So if you want to determine bulk fields, then it has been clear, at least since the 80s, work of Belavin, Polyakov and Topological, but also many others, that you have to solve associativity constraints. So you have to look for certain algebras. Then these algebras have been attempted in the 80s and the 90s to classify them based on the modular data, so on the S matrix and on the T matrix. And in nice cases, this has led to ADE classification, but in the mid-90s, it was clear that classifying modular partition functions is really not the good thing to do, because quite a few of the modular invariant partition functions are definitely unphysical, and even worse, it's very difficult to detect whether a modular invariant partition function is physical or not. Well, then in the 2000s, it became more and more clear that in the semi-simple case, you can construct a full local rational conformal field theory in which left movers and right movers are combined from the additional datum of a module category over it. In fact, a rather specific one, a semi-simple module category that is indecomposable, or alternatively by prescribing certain symmetric Frobenius algebra. Well, in this talk, and this is probably the first talk in our workshop, it will be important that I will not insist in semi-simplicity. So I will use the power of category theory, which is already incredibly useful in the semi-simple case, to extend all these constructions beyond semi-simplicity. Of course, I have to keep something to have a well-defined mathematical framework, and what I will keep are still certain finiteness properties. So what is my plan for today? I want to take you on a big tour, and I will start in a field of pure mathematics. I will talk about some things in classical representation theory of finite dimensional algebras, and you don't lose anything imagining finite dimensional algebras over the field of complex numbers. And there will be nothing like Hopf algebras or categories with a tensor product like fusion categories or their non-semi-simple cousins. Only in the next part, I will go to monoidal categories and module categories over them and develop tools which in the end will give me a very compact description of bulk fields in two-dimensional conformal field theories beyond the semi-simple case, beyond rational CFTs, if you incorporate the word semi-simple in the word rational. So the next part of the talk is in principle in pure math. It is about representation theory of finite dimensional representations of a finite dimensional algebras, and it is some very classical stuff. So take a field, the complex numbers is fully enough, and then we look at a class of categories which I could informally describe as a category that is equivalent to the category of finite dimensional modules over a finite dimensional algebra. And for these categories, there is some intrinsic characterization. So there are nice finiteness properties. So every object has a finite length, there are enough projectives, and there are finitely many isomorphism classes of simple objects, but we do not require that that any object is a direct sum of simples. And a finite tensor category is then, that's what we are going to use a bit later, is a finite category that is monoidal and moreover is rigid. So we have left duals and right duals that will enter quite crucially at the technical level. For example, the tensor product functors in our context will be always exact. Okay, so now there's a classical fact of algebra which dates back to the 1960s, and it's the following thing. Suppose we have two of these categories, A mod and B mod, and we want to describe functors. Well, in this situation, you shouldn't look at all functors, but at right exact functors. So, now any of such a right exact functor, so this shouldn't be tensor, this should be functor, can be written by tensoring in the form of tensoring with some bimodules. So right exact functors are all of the form tensoring with some bimodule, and the bimodule can be obtained pretty explicitly in terms of the algebra A and the functor. And there will be a complete symmetry in this first part of the talk between right exact and left exact functors, and there's a similar expression of getting left exact functors in terms of bimodules using not a tensor product but a hom. Well, okay, so this is a nice classical result, but it's not terribly useful for conformal field theory because typically we want to discuss things in categories of representation, say over vertex algebras, and not over some finite dimensional complex algebras. And then we have just a categorical world, but not a very explicit algebraic world. So it's much easier to work than in the categorical world. Okay, now the first part, I want to explain to you how to phrase this Eilenberg-Watts theorem in a categorical way. And what I want to do is I want to relate left exact functors, right exact functors, and bimodules. And these bimodules, they are described in terms of this product of tensor categories, in terms of the so-called the linear product of tensor categories. Well, the linear product of A mod and B mod is A tensor B mod. It can be characterized by some universal property as any decent tensor product should be. And before explaining what is functors here, psi L and phi L, phi R and psi R are, they will be adjoint equivalences. Let me look at some tool we will need a lot in the sequel. So I need co-ends and their dual version ends. So for the physicist part of the audience, we are all used to implement something like sum over states. And if you think about state sum models, as we have seen them in Jürgen's talk, in the semi-simple world, you would sum over all irreducible representations. Well, not all irreducible representations, but all irreducible representations up to isomorphism. What is the co-end? Well, informally speaking, the co-end is a sum over all representations up to all morphisms. And this is a notion that makes a lot of sense even beyond finite semi-simplicity. So what we do is we take the sum over all objects. For example, if I want to take the co-end of X dual tensor X, that's of course a huge object, and we mod out, roughly speaking, all morphisms, and this is defined as a quotient. What you should keep in mind is that a co-end is a variant of a direct sum, and we teach our students in the first year in linear algebra that morphisms out of a direct sum are characterized, are the same as families of maps into the direct sum. And of course, families of maps. And there's a fundamental thing in category theory, which is you can reverse arrows. If you reverse arrows, then you get a sub-object of a product. And a sub-object of a product that is defined in an analogous way is called an end. And the integral notation is standard in the mathematics literature. It is very well justified. For example, there is a Fubini theorem for ends and for co-ends. Well, you have all seen ends and co-ends. For example, the trace is just a co-end. So if you take the trace in the category of, say, finite dimensional vector spaces over a field K, then this must be a vector space. Well, there are not so many distinguished vector spaces. So this is the vector space, which is the ground field itself, and it must come with a morphism as the direct sum does. This is a morphism from V tensor V dual. So these are endomorphisms of V to K, and this is the trace. And all the properties of the co-end, the universal properties, are things you learn in a more elementary language when discussing properties of the trace. What's also quite important is that you can write natural transformations of between two functors in terms of an end. Indeed, an end is a subspace of a product. A natural transformation is characterized by its component. So it has many components in a product, and they obey certain relations which single out a subspace, and that's what the end is. And so this formula of natural transformation is something I would write to a blackboard in Vienna and leave it for the rest of the talk. But here we don't have blackboards, but you have the transparencies as a PDF file. So please keep this formula here in mind. Well, now I said that the end or the co-end behaves very much like an integral. An integral should have something like a delta function. And indeed, the Hom behaves like a delta function. So if I take any functor G and any linear functor, and I tensor it here with Hom, then I get back the functor. So that's a decomposition of the functor in terms of a co-end. And the Hom is something like a delta function. Now, our Hom spaces have been finite. That was a finiteness condition I was highlighting. So it is innocent to take the dual of as a vector space. And that's what I take here. And then you get a similar construction of for the end, that the dual of a Hom space behaves like a delta function for the end. And indeed, in this talk, and very importantly for bulk fields, we have to be aware of the fact that the Hom has some relative, which is the dual of a Hom. Okay. And to give you some usefulness of these notions, maybe most of you are probably familiar with the Peterbilt Theorem, which expresses the space of functions on a Lie group, say, in terms of irreducible representations. Well, in terms of the end or the co-end, you can write down a Peterbilt theorem also for finite dimensional algebras that are not necessarily semi-simple. In this case, of course, you cannot expect that A as a bimodule can be written as a direct sum of simples, but the end or for a dual, the co-end give a very good expression that can be easily manipulated. And that's what we are going to manipulate in a moment. So I want to explain this Eilenberg-Watts calculus. So I want to relate left exact functors, right exact functors, and here, this is my categorical replacement of bimodules. An A module, well, the opposite actually of it, tensored with B, so the opposite here turns left modules into right modules. Now, how do these equivalences look like? Well, let me just flash the equivalences. They involve, for the left exact functor, the Hom, which famously is left exact. For the right exact functor, the dual of the Hom, that's something you should keep in mind. And then the inverses are defined using essentially this Yoneda version of the Yoneda lemma in terms of co-ends and of ends. Now, look at this diagram and imagine for the moment that A is equal to B. Then we have endofunctors. Endofunctors can be composed, so this is a monoidal category. And there is a distinguished endofunctor, which is the identity. It is quite important that if you go from the identity as a left exact functor, you turn it into a bimodule, and you turn the bimodule into a right exact functor, you don't get the identity as a right exact functor, but you get a functor, a right exact functor that's very famous in representation theory. And indeed, what you get is this functor here, which is called the Nakayama Functor. It is defined here in this, in terms of this co-end over the dual of a Hom. And of course, there's a dual definition, which gives a left exact functor. And if you compute what it is in case of the representation category of an algebra, it is the classical Nakayama functor you can find in textbooks. So you investigate these functors, you see that they are adjoint. You can study the case when they are actually equivalences of categories. And what's quite important for our talk is that if the Nakayama functor is trivial, and if A is the category of modules over an algebra, then indeed this algebra comes with the structure of a symmetric Frobenius algebra. So we have a categorical way of talking about symmetric Frobenius algebras. This is one thing. Now, for bulk fields, I need one more observation, namely, if you take here the image of the identity functor is a left exact functor, you can write it as a co-end, but using the right exact part of the Eilenberg-Watts calculus, you can also write it as an end. It's an end, and there is a twist here by the right exact Nakayama functor. But the important thing is that we relate an end and a co-end, so very roughly speaking, something like a direct sum and a product. And that will be important to get co-multiplications and multiplications on bulk fields in a moment. Okay, so now this was the first part. So far, I should emphasize no monoidal categories, no Hopf algebras, everything in the realm of finite abelian categories or finite dimensional algebras and their finite dimensional representations. So I have now to introduce some additional structure, and this is the following thing. The notions were already mentioned a couple of times. So a monoidal category is something like a monoid in categories. So you have a tensor product. And if you study monoids or algebras, you want to study modules over them. So module categories are categories together with a mixed tensor product, which allows you to act with an object of the monoidal category on an object in the module category. And of course, you can also act on morphisms. And already in Jürgen's talk, well, there are left module categories, right module categories, bimodule categories, and then you can define module functors, module natural transformations in a rather obvious way. A very important example that will be related to the Cardi case in CFT is the case when that any monoidal category is module category over itself. In fact, a left module category, a right module category, and a bimodule category. What we will use is that it is a left module category over itself. Okay, the module categories I'm going to consider are finite module categories, but they are not necessarily semi-simple. And so they have, again, finitely many simple objects, but not necessarily, it's not necessarily true that any object is a finite direct sum of simples. And the action obeys several nice properties. Now, a very important notion we need from category theory to understand these bulk fields is the notion of an internal Hom. So if I have a module category, then M is a module category, then the internal Hom is an object in the monoidal category. And it is an object in the monoidal category that is defined by saying that the Homs from any C into the internal Hom is given by this space of Homs in the module category. So this is a way to obtain objects in the monoidal category, and in fact, much more than objects. It turns out that these internal Homs behave very much like objects you know. So for example, let's take the monoidal category of supervector spaces. So these are Z2-graded vector spaces with a certain braiding. The Homs, the ordinary Homs in the category theoretic sense, are grade preserving linear maps, but the internal Homs are themselves supervector spaces. So these are matrices that have even components and odd components, and everybody who has calculated with some superstructure has implicitly used internal Homs in this category of supervector spaces. And what is important is very much as you can compose Homs, you can compose internal Homs, and they are associative. The composition is associative, of course, associative with respect to the associator of the monoidal category C, because the internal Hom is an object in the monoidal category C. Okay. So now this is a technical slide, but it will be quite important. I've explained to you in this section where there was no monoidal category, and this is in principle a proposition that belongs to this section, that the Nakayama can be seen as kind of a relative of the identity functor. The identity functor famously commutes with any functor f. The Nakayama functor, because also the composition is changed, doesn't commute, but if you commute it, you have to take a twofold left adjoint. And of course, you have to assume that the twofold left adjoint exists. And then you can see that if you're commuting any functor past a Nakayama functor, it gets a twofold left adjoint. And actually, this is a famous, leads to a famous generalization of a famous result in Hopf algebras, namely the Nakayama functor. If I'm looking at a bimodule category, well, the Nakayama functor on a bimodule category, I can act with an object of A on the left or with an object of B on the right. And if I pull it right out of the Nakayama functor, I get biduals. This is actually the left adjoints I have here, and it follows from this theorem. And then it's a rather straightforward calculation, which I probably won't go into too much detail, to show that if you specify to this case, which I mentioned earlier, namely that the finite tensor category is a bimodule over itself, that then if you notice that this, the value of the Nakayama functor, the monoidal unit, is the distinguished invertible object, the one that classifies integrals of a Hopf algebra, then computing this in two different ways and using that A is equal to A tensor 1, you see that these two expressions are equal, and you recover that conjugating with this distinguished object gives a fourfold dual. That's, of course, categorical version of Redford's S to the fourth theorem. Now, why is this important? We're going to use this in a moment. Now, I want to define Serre functors. So I define it in the following setting. I take a module category over a monoidal category, and then I want to relate Homs, duals of Homs and Homs. That's how you define a Serre functor. Now you can say an ordinary Serre functor, well, there is no inner Hom. You just take the ordinary Homs, and this is in standard algebra not a very interesting notion, because Serre functors exist only if the algebra is semi-simple, and if you want to have Serre functors in more general settings, you have to go to derived settings. Here, I'm not comparing Homs, but I'm rather comparing inner Homs. And then it turns out that such Serre functors exist. Such Serre functors exist for a famous class of module categories, so-called exact module categories. They have an intrinsic characterization. They are have been classified, for example, if you realize module categories in terms of module algebras over a Hopf algebra. And you can show that their functors are equivalences of categories and they are twisted module functors. Twisted module functors means that if you have an action by an object in a monoidal category and it travels out of S, it gets twisted by a bidual, a right bidual or a left bidual. And actually the Serre functors are closely related to the Nakayama functors. So, well, they are twisted module functors, and now there's an important thing: trivialize Serre functors. That's something that probably anybody who has seen some advanced course on algebraic geometry has come across. So what do we mean here? Well, if we want to trivialize, we want to say the Serre functor is the identity functor, but it's a twisted module functor, and the identity functor is not a twisted module functor. So this only makes sense if we can trivialize the bidual. And this is what one calls a pivotal tensor category, in which an object and its bidual can be identified, and that's structure. And then a trivialization of the Serre functor is called the pivotal structure. That's essentially trivializing the Serre functor as a twisted module functor relative to the pivotal structure of the monoidal category. Okay. It should be emphasized that for the monoidal category, the pivotal structure is structure. For an indecomposable exact module category, by some Schur's lemma type argument, it is essentially unique. It is unique up to the scalar. So it is a property. Okay, this is what I need to discuss bulk fields in two-dimensional local conformal field theories. And the setting I'm now going to is finite categories with more structure. Still, they are not necessarily semi-simple. They are finite in the sense I have defined. They are braided, and the braiding is non-degenerate. So there's one property that which also appeared in Wen's talk, that the Müger center is trivial. There are other characterizations of a non-degenerate braiding. For example, that the Trinfeld center can be written is braided equivalent to C, the linear C with the opposite braiding. And all these characterizations of a non-degeneracy of the braiding are known to be equivalent. And it is known that categories of suitable vertex algebras lead to modular tensor categories. And there are also a couple of more sources. In any case, think about this modular tensor category as axiomatizing the chiral data, the Moore-Seiberg data, of a conformal field theory, a chiral conformal field theory that is not necessarily semi-simple, but still has finiteness properties. Of course, the semi-simple case is contained here. That's a special case. Now, what do we know about fields? Well, fields in a two-dimensional conformal field theory, they should transform in representations of the chiral algebra, so they should correspond to an object in our category, and they should be obtained in the case of bulk fields by combining left movers and right movers. So they will be ultimately objects in the Trinfeld center, and they are OPEs. So they should be, the OPE gives them an algebra structure and even a bit more a Frobenius algebra structure. And the pictures I've stolen here, they are from Levellen's 92 paper. And the modern way to express it is to say that the bulk fields should form a Frobenius structure, and the boundary fields should also form a Frobenius algebra, a symmetric Frobenius algebra. So how do we get them? Starting from a finite modular tensor category plus some additional datum. Well, the additional datum, and that's essentially what we learned in the 2000s, is a module category, a suitable module category over the modular tensor category. So the interpretation of this module category is that the boundary conditions are objects of this module category, and the boundary fields, which can change a boundary condition M, object in calligraphic M, to a boundary condition N, they are given by inner homs. Inner homs are objects in C, so no left movers and right movers combined, that's okay. And the OPE, which should be associative, is just the composition of inner homs. But remember that we should get not just an algebra, but a Frobenius algebra. So for this reason, we require M to be a pivotal module category, because there is a proposition which states that if you look at a pivotal module category, then the inner hom, or the inner end, to be more concrete, is not just an algebra by composition, but it has a Frobenius algebra structure. This is something which developed in several steps, and it's most notably related to the work of Schaumann and of Shimizu. So, it is therefore clear that we can get a good theory if we go to pivotal module categories. So module categories which admit a Serre functor, in which the Serre functor, which is essentially up to a scalar property, can be trivialized. So now what do we need to do? We have to take a pivotal module category and we have to extract from this an algebra describing bulk fields. And this is an algebra which combines left movers and right movers. And due to the fact that this is a modular tensor category, it should be an algebra in the Drinfeld center. So we should obtain a Frobenius algebra from the boundary data, and we should get this not only for the bulk fields, but there are many more fields in a conformal field theory. There are defect fields and disorder fields, and we should get algebras for all of them. So let me explain how this goes. Now, the situation is now, the most general situation is now the following one. We fix the chiral data once and for all, and they are described by a finite modular tensor category. So this includes certain types of logarithmic conformal field theories. Now, how to combine left movers and right movers, that's described by M1, which is a pivotal module category over C. But there can be different pivotal module categories, and you can consider local CFTs labeled by different pivotal module categories, and that are separated by a topological defect. Well, such a defect needs labels, and it is a very obvious idea to choose as labels right exact module functors. So we have here a defect of type F, which is a right exact module functor from M1 to M2, a defect of type G, which is another module functor, and we need to produce from these data some object in the Drinfeld center, which has the property that, for example, if F is equal to G, we get a Frobenius algebra. Now, how to do this? Well, maybe we first look at this picture. If we take the Poincaré dual of it, you get something which looks pretty much like the standard picture you see in category theory to describe natural transformations. So probably the thing we are going to do should be related to natural transformations of functors between module categories. So they should be related in some way to module natural transformations. Well, actually, let's start a discussion from a slightly different point of view and come back to this picture in a moment. Yeah, let's note that this category of right exact module functors is itself a module functor. It is a module functor well, you could try to turn it into a module functor over C by simply acting with C on the result of applying a module functor f on M1, but then it's not a module functor. You need some more structure to get the structure of a module functor in it, and that's precisely a half braiding. So these functors are actually, in a natural way, a module over the Trinfeld center. And the Trinfeld center, or a pivotal category, is itself pivotal, and we will always take it with this pivotal structure. So what do we want to take? We want to now consider internal homes over of this module category Rex over the Trinfeld center. And let's investigate this. Well, the following formula is incredibly useful. In the beginning, I said there was a formula that I would have written on a blackboard in Vienna, and that would have stayed for the whole talk. And this formula was a formula for the natural transformation between two functors. And so take this formula here without the underscore, forget about this in the Trinfeld center, and then we would have taken the end of Homs. Now what we do is we can show that this object not in Fg is actually, well, it is an equal to also an end, but an end where the ordinary Homs are replaced by inner Homs. And yeah, so this is the formula for the natural transformations. And if you modify it, you get a natural source of interesting objects in the Trinfeld center. And let's first go a little bit back to the case where of ordinary natural transformations. If you do it for a category of modules over an algebra, then the natural transformations from the identity functor to itself are the Morita invariant way of expressing the center. And so this here is an expression for the center of an algebra. What you see is that if we put f and g equal to the identity functor, this would be a transparent defect. Then we get something like an internalized center, and that's the bulk algebra. Now, this really behaves like natural transformations. Natural transformations can be composed vertically, but they can also compose horizontally. And the same is true here. And they obey the relations you expect for natural transformations. In particular, you can apply an Ekman-Hilton argument, and this Ekman-Hilton argument implies that this, or rather an analogous thing for the bulk algebra, is not only an algebra, but it is a commutative algebra. So we get a nice source of algebra. For conformal field theories, rather than algebras, we want to have Frobenius algebras. So let's see how to get Frobenius algebras. Now, there is a variant of this Eilenberg-Watts calculus, which uses which doesn't apply to functors, left exact functors or right exact functors, but to right exact and left exact module functors. And then you have to take here a category which is the linear product plus some balancing. Well, if you go through this diagram, you get again a relation that identifies an end and a co-end. So that here we have a source to get a relation between ends and co-ends. Co-ends famously want to be co-algebras, ends want to be algebras. We can identify them. So this is already half a way to go to Frobenius algebra. More complicated, and these are the recent theorems which prove what I just informally try to announce. So suppose we have a pivotal finite tensor category, and if C is modular, then it has a distinguished pivotal structure. And M and N are exact for C. The category is an exact module category, and one can compute its relative Serre functor. And the relative Serre functor can be expressed in terms of the relative Serre functors of n and m, and distinguished object for the monoidal category C. Now, the distinguished object is not so important if you're interested in modular tensor categories, because in this case, D is isomorphic to the monoidal unit. Now, the second thing you can show is that if this is unimodular, which is true for modular tensor categories, and if M and N are not only exact but pivotal, so if they have trivial Serre functors, then also the right exact module functors are a pivotal module category over Z of C. And now we can invoke Shimizu's general theorem, which says that if we take inner ends in a pivotal module category, then these are not just algebras, but they have the additional structure of Frobenius algebras. And in the case of the special case when F is the identity functor, then we have a commutative symmetric Frobenius algebra, and the fact that I'm saying commutative symmetric is not doubling things, but in the braided setting one has to say the two words. So these are very good candidate for bulk fields, as I want to explain on the last slide. Before explaining this, let me mention that if you apply it to the case where C is semi-simple, then a pivotal module category is necessarily semi-simple. You can compute, for example, what these internal natural transformations are, and you will find formulas for this object, which are exactly the one for bulk objects that have been derived in the TFT approach to RCFT correlators almost 20 years ago. But here, no mentioning of semi-simplicity. This works for logarithmic CFTs as well. And once you get used to these categorical tools, also the construction, in my opinion, becomes more transparent. Okay, so now let's go back to the 92 paper of Llewellyn. So this is, all these drawings are stolen from Llewellyn's paper. Well, Llewellyn says that if you want to construct open-closed correlators, and he has a single boundary condition, but that's a minor detail, you have 3 building blocks. So that's the way he phrases them. Well, this here is the product for the bulk fields, but of course we can read it this way and this way. So it's a product and a co-product, and they have a Frobenius algebra structure. Then you have a similar thing for the boundary fields. That's also a Frobenius algebra, because we have them realize them as inner homes of a pivotal module category. And then there is an amplitude which allows you to go from a boundary field to a bulk field. Now, in our situation, we have natural transformations which are characterized as an end. As a consequence, we have really structure morphisms of an end, which give us something like components of a natural transformation. And so we have morphisms which go from the bulk field to hom MM, which would be boundary fields that do not change the boundary condition M, but transform it into the boundary condition M itself. So we have this a natural candidate for this building block in Llewellyn's paper. First, since it's an end and a co-end, we have also arrows in the other direction. So now in Llewellyn's paper, you also find these consistency conditions. Here, A was already on a slide. That's the fact that bulk fields are Frobenius algebra. That's now for this formula for the bulk fields, that's a theorem. C means that the boundary fields are Frobenius algebra. Now, let's look at the other things. So what do we have? We have, for example, E, and then you see that here you first take the component maps and then you multiply open strings or boundary fields. And here you multiply bulk fields and then you take the component map. But that's quite easy to understand because the vertical composition of natural transformations is defined component-wise, and it turns out that this holds for these internalized natural transformations as well. So E is kind of very automatic. And the same applies also to D. If you see here, you have boundary condition A and B, and their role is exchanged. And actually, that's a consequence of the fact that our end or co-end enjoy dinaturality properties. Admittedly, B and the last thing, F, so-called Cardi constraint, they are more complicated. They don't follow from what I said. That's still an open problem. And you see here that these are genus 1 constraints. They are much more complicated to deal with. That's almost already the first comment in the outlook. Of course, one of the things you want to do with this very nice algebraic structure is you want to describe then correlators and use modular functors with various formulations of modular functors, state sum, string nets. We have formulations of modular functors for Reshetikhin derived type and even their non-semi-simple variants due to Lubachenko. And all this can be used to explore then correlators. And of course, rigidity was technically important here, but for CFT, interesting cases without rigidity for the chiral data, and the formalism should be extended to them as well. So this was essentially what I wanted to tell you. Thank you very much.